Thank you everyone for joining us this evening. I know we're the last talk before the fun begins. So what Soila and I are going to talk about is bringing your own models, and essentially it's machine learning as a service. So we know models are everywhere, there's machine learning everywhere, whether it's genomics, finance, supply chains, even fixing high voltage wires somewhere. But today we're going to tell you a little more about autonomous vehicles. So we're going to tell you a little about our data center platform. Intel's also in the space of autonomous vehicles, along with Waymo, Uber, and a whole lot of other companies. We have two approaches. One is creating our own autonomous vehicles, and the other is assisting vehicle vendors with their autonomous solutions. So our data center platform is really for research and development, and we have a fleet of cars that go out and drive and collect a lot of data that they save on SSDs in the trunk of the car. Once that data is collected after a 4-hour drive session or 8-hour drive session, they come into a garage where the data is offloaded and moved into our data center. So if you have a data center close to the garage, it's a simple process of sneaker net. You move this onto an ingestion station, but if they were remote, you could even put them in a suitcase and mail them, as long as the suitcase is ruggedized. So in the data center, what happens? First of all, we ingest the data, that's really copying it over, saving it in any one of warm, hot, or cold storage, depending on our need. And then starts the whole process of parsing it and then running any machine learning training or inference, and eventually simulation, where we want to test out our models, our planning, and our actuation. So you have a digital car that you can load onto the vehicles, and they can drive around, and hopefully everything is safe. Otherwise, rinse, repeat till we get things perfect. So given this data center, let's kind of take a look at the kind of data volumes that we are encountering. In this space, you can have anywhere from 1 to 20 terabytes of data per car per hour. That data volume depends on the number of sensors in place, the kind of resolutions the cameras provide. Sometimes you have a lot of high definition cameras. Some of them might be lower definition. You have LiDAR, and maybe not just one LiDAR unit, but multiple LiDAR units. And then there's also your GPS data. So there's a slew of data out there, and this is to help make your car safe under different environmental conditions, under different lighting conditions, and to give you advance warning. So let's take a look at our data center platform itself. We are using Hadoop. We have Ceph 2. We have a variety of hardware, from GPUs to FPGAs, and then we're also looking at some newer chip like a Movidius chip. And in this data center, we have to do different kinds of workloads, from machine learning training to machine learning inference, simulation, all that parsing. Remember, we have those huge amounts of data. So we want our resource pool to be fungible, so you can run different kinds of workloads on the same resources. Further, we want our workloads to parse and be complete and be done, so that you can put those vehicles back on the road to go and collect more data. So we want our workloads to be dynamic, fast, and resilient if something crashes, to restart itself. Because these are high commodity servers, so there's all this resiliency through multiple instances running. And we want everything to be easy to use. Now in this space, can we make bringing our own models just as easy, just as reliable, just as resilient as the rest of our platform? So those were some of our criteria in our design process. So what kind of models do we have? We have lots of them. There'll be some for just camera data, there'll be some for LiDAR, there'll be some for sensor fusion, where we combine camera data and LiDAR data to get better inferencing, better detection. We have also certain government regulatory related models. You want to detect not just a pedestrian, but the face of the pedestrian to obscure it, to maintain privacy for anonymization. We might also have models within our simulation process, because that's really the digital car. You want to do end-to-end, everything that those sensors are detecting and how you want to plan and actuate according to them. So what are the parameters we want to save along with our model? Not only do we want to know that this is a model that applies to camera data, we also want to know what version of this model, because we are going to be incrementally improving upon them. What training sets had we used? What test sets did we use? What kind of accuracy and precision does it provide? But also whether this model runs on an FPGA or on some other kind of processor for higher speed and throughput. So these are the kind of parameters we want to save along with our models. So let's just take a look at the rest of our platform. Not only do we have data sets and then the usual CRUD operations with our data set, but we want to have different pipelines for these data sets. Like first, come along and parse it, and then maybe detect those faces. Then the next step might be blur the faces, so on and so forth. And not only that, part of this whole process is when you get an image, you might have to do some pre-transformations on them. The pre-processing could be resizing it. It could be compressing it before storage, maybe decompressing it, maybe encrypting it if this is some very personal data. So along those lines, we want to support models in this bring your own model story, on this journey of bringing your own model. We want to support CRUD. We want to support validation of any dependencies that it has. Suppose you have created a model that's for TensorFlow. We want to make sure that your TensorFlow framework is at the right version. So the other pieces are very standard, like name, description, the framework, so on and so forth. And they're tags. Sometimes a model is just research or it's only internal consumption. Please do not apply in production just yet. So these are the aspects that we want to cover in our Bring Your Own Model story. With that, I hand off to Soila.
Okay, thank you so much, Malini. So our current platform is on bare metal, and what this means is that we're running most of our stuff on Spark with Yarn. And one of the issues we run into with different kinds of models is maintaining all those dependencies. So one person wants to run TensorFlow version, 1.8, someone else wants to run TensorFlow version, 1.2, maybe the versions of GCC they need are different, the MKL optimizations they need are different. And so what we're looking at is how do we migrate from this bare metal platform into a more containerized environment using Kubernetes. And we're looking at using Spark on Kubernetes, and this is something that Intel has been actively contributing to as well. So the model deployment pipeline has two stages. One is the model creation and registration, and the other is running scalable inference pipelines. So a user would bring their own model by defining it by creating a Docker image that contains the model and pushing it to a Docker registry. Along with that image, they would provide additional model descriptors, for example, what framework that model is associated with, and whether there are any hardware preferences when we're doing scheduling. For example, is this a CPU version of a model or an FPGA version of the model? And all this data gets stored in a model catalog. So once we've created the model catalog, the next step is to run a scalable inference pipeline. And as Malini mentioned, these autonomous vehicles just generate a ton of data. This sensor data is typically in some kind of specialized format, either ROSBAG or MDF4. And these are hierarchical file formats that organize the sensor data by type and by timestamp. So in order to use this data, you have to do some pre-processing just to parse it, to synchronize the different sensor streams. So if you have LiDAR point clouds coming in, you have your camera images, you have to synchronize those and apply other pre-processing steps. Then the next stage would be running inference using some kind of pre-trained model. So for example, a user may want to run a pedestrian detection model on the camera data. And they may want to apply some post-processing steps, such as blurring the faces of pedestrians in order to preserve their privacy. And then this data gets stored in some searchable data store. Right now we're using Solar for that. And this helps us to support queries. So a user can say, we want to find all the images that have pedestrians at crosswalks. So we are looking at two different deployment approaches when we migrate to our workloads to Kubernetes. The first one that we're looking into is just using this kind of monolithic container where we have the Spark executor and all the model dependencies all bundled up in this large container. And we could just execute this with Spark on Kubernetes. The pros of this approach is, one, it's pretty simple to deploy, and the container lifecycle for your Spark application and your model are completely in sync. You don't have to think about version tracking between your ML framework and your model and your Spark engine. And you have data locality because the model is contained in the same container as the executor. The cons of this approach are, one, a really large container footprint, and there's really tight coupling between the model and the Spark engine, so it makes it difficult for us when we think of supporting different frameworks. So the next approach that we're looking into is something we're calling just-in-time composition. So in this approach, instead of having this huge Uber container with all your kind of model binaries, what we do is run the Spark service and the inference service as separate services on Kubernetes. And so the Spark application ends up being a really thin client which in our case maybe is using an efficient protocol like communication protocol like gRPC. And this application will call out to the inference service that contains both the ML framework and the model. And the inference service will respond back with a gRPC request to the Spark application. The advantage of this is we support a common API between the Spark service and the inference service. So this will make it easier for us as we move from one machine learning framework to another. So for instance, currently, let's say we have TensorFlow and we want to move into Caffe or some other custom model that the user wants to provide. So one of the advantages is, one, the small container footprint, and the other is we get auto-scaling with Kubernetes, and the standard API, as I mentioned, just makes it very easier for us to switch the inference service. The con is that it's pretty complex. Now you're orchestrating two services and you have to start them up and stop them together. And the other thing is that we lose the locality, and we have to think about what is the cost of these remote calls to the inference service. If you're dealing with lots and lots of data, is that going to be very expensive? Do we have to take advantage of some of the mechanisms that are already available in Kubernetes, where we can co-locate pods from different applications on the same node, and therefore reduce the latency of our inference calls? So we have a prototype that we've developed using the Spark on Kubernetes operator. This is available through the Google Cloud platform. It is an experimental, it's in the experimental stage, so not yet production worthy, and some of the APIs may change. We noticed we still don't have support for persistent volumes unless you enable some alpha features in Kubernetes. But for the prototype, it is sufficient. And the other reason why we went with the Spark on Kubernetes operator rather than using the Spark submit client is because it made it easier for us to use other Kubernetes application and chain them together in our pipeline. So for the prototype, we support both Spark streaming and batch mode. And in this example, we would have our sensor data being streamed into a Kafka input topic, and then we would run our any pre-processing steps, inference and post-processing using Spark, and then the output is submitted into a Kafka topic. So I will show a brief video just demoing the prototype. One of the things that you might want to do is list the models that are available in your framework. So we just picked some models from the TensorFlow Object Zoo, so it's just some generic models. And then after that, you might want to create a new model. And what we'll do with this is we'll just use an existing template, an existing model, just copy paste for the demo. And the next thing is we will delete some of the auto-generated IDs, and we will modify the name of the model and also the location of the model. Sometimes your model might be mounted on a persistent volume in this case, or it might be just bundled in the model. So this is changing from an object detection model to a license plate blurring model. Okay. And we send this request and we get a response back, which shows that you've registered the model, you have a new auto-generated ID. So once you have an auto-generated ID, you might want to build, a new pipeline. So for this particular demo, we'll just use the pre-canned pipeline. And what this application is doing is reading in from the Kafka topic, running inference, and writing the tags back to a Kafka topic. So we modify the model ID for the pipeline and execute it. When we click send, what happens is we trigger a Kubernetes job, this is implemented using the Spark on Kubernetes operator. And if you're a DevOps person, I know for users, maybe you don't want to see this, but if you're a DevOps person, you're like, oh, I want to see how my Kubernetes application is doing, how many applications do I have running. You might want to describe the application, so you would say the namespace, and you would give the application name, and this is more for DevOps people. Just say, okay, I have all these executors that are running on Kubernetes, and it has this particular driver, and everything is okay. And another thing you might want to do is debug your Spark application, and you just get your logs. You could just look at the driver pod and just look at the logs. So the last thing we did is just visualize. You could visualize the stream of data. So we just had, this is just someone driving down the road. We were hoping we could get the O.J. Simpson car chase or something, and just, label his Bronco on, I can't remember which highway. But essentially what you have is just a simple pipeline that we've done using Spark on Kubernetes. And so it gives you some idea of what we're thinking about as we try to migrate from bare metal, to a more containerized workflow in the data center. And with that, I'll hand it over to Malini to talk.
So hi, everyone. This is just a little bit of wrap up. So what we do know we need to focus on for the immediate future is support our just-in-time composition. And a part of this will, of course, be having to take care of any dependencies. So when somebody wants to upload something that requires another version of the framework, we have to ensure that we have that framework in our environment. A very important thing is also about resource scheduling. When we're talking resource scheduling and you have a heterogeneous collection of hardware, do you want to run this model on any end any available host, or do you want to run it on a host with FPGA or a GPU or whatever? There are pros and cons in this, like the model that you have to use should be targeted to the hardware, the amount of latency, the speed, the accuracy that model might give. So you might want to use those in determining the number of pipelines that are possible, and among the pipelines, which one you want to choose. So those are hardware-related scheduling that we have to take into consideration as part of future work. And last but not least, what does this entail for us for a wrap-up today? We'd like to say that bring your own models is an important item that we all need to focus, not just on our research and development platform for our autonomous vehicles, but I'm sure this is something that researchers would like to do too. Essentially, it's data. Data is the big thing. Data is the hard thing to move. And let's say you have some genomic data and another university has some other data. You might want to be trading models, exploring your accuracy on your data versus their data, and be able to make a partial order on these models, like, hey, this model is better, or it handles these sort of environments better, type of thing. So I see not just data exchange going forward, but a lot of bring your own model, explore our models, be able to categorize and classify our models in their performance and accuracy. Last but not least, we're bringing in two different kinds of brains and sets of expertise here. We have the DevOps kind of brain capabilities and strengths, where they have to keep this data center, whether it's a research development environment or a production environment, alive and working, and do so reliably, scalably, be dynamic. And then you have all the machine learning expertise, and often they're not in the same head. So how can we make these two different bodies of people work better together and be more productive and scale? So that's where bring your own models is important. We want to provide an API so that the machine learning people can toss over their wonderful models, improve them, test them, use them at scale. And that's pretty much how our teams also in our data center work are operating. We have Soila, who's a machine learning expert, and I have some cloud background, and we wanted to bring these two groups together to be more performant. So that was the motivation behind our work, and we urge you to focus on this. Thank you. So we're open for any questions. I know we're keeping you away from the evening activities, but we're here and we're happy to answer any questions.
Regarding the model files itself, the artifacts, so how are you versioning it? And model files, it's going to be PMML, or do you have specific requirements in terms of how the model should look like?
So right now we do not want to constrain the model format. So you could have a PMML format, which is more an kind of an open format, but for deep learning models you could have ONNX, but we don't want to constrain the model format, so that the user can feel free to use whatever model format they want. All we'll do is have that model in a container that exposes a standard API that we can talk to over. You can think of it like REST. Yeah.
Any plans to use Mesosphere? Mesos?
Mesos? No.
No, we were just thinking of Kubernetes right now.
So what the reason you choose Kubernetes instead of Meso? They say the Meso is more mature than Kubernetes when you use a Spark.
Our motivation was the amount of adoption for Kubernetes is pretty significant, and there's a very large community working on it. Further, all these other frameworks from Google like TensorFlow, etc., work with Kubernetes. Docker containers is easy, but Mesos also supports Docker containers. So that could be future work, but we just went with Kubernetes given the status right now.
So far you use Kubernetes, you have any issue? No?
We have used Kubernetes in our environment.
Yeah, you happy with it? No,
we have other groups at Intel that have used Mesos, but our team has basically used Kubernetes.
Thank you.
So you say right now in your prototype you have the monolith container with the ML framework and the Spark in the same container, but you want to get to the point where you're separating it out? Is that correct?
Yeah, right now. So the demo I have is with Spark, the model in the same container, but we also have a prototype where it's separate. Yeah, it's just that we haven't tested it, and what we need to do is test it and see which one scales better before we make a decision on what option to go with.
See, do you plan to publish anything about those results from the test?
What?
To publish results?
Oh, well, we aren't yet at that stage, but yes. So one of our things with the gRPC call was like it can take anywhere from 3 to 4 milliseconds. And sometimes it looks like having the data locality will be very important given our data volume. So that was like the tension between having the monolithic model versus this, broken, separated entities, the just-in-time composition. But an advantage of the just-in-time composition is it can auto-scale, and not only one pipeline needs to use it, but multiple pipelines could be using the same model, and then that can auto-scale and grow and things like that. So, and Kubernetes gives you all that for free. It does all the auto-scaling, resiliency. If something dies, it just creates a new instance of the container.
So I just want to add to this thing because
just jump the line. You go ahead.
Sorry.
After you.
So I'm also from Intel, from a different group, but we also prototype the similar model, but model itself will be S3, and the container images will just be framework specific. So that's yet another layer of abstraction that you can add there, and that will allow a little bit better model provenance and model versioning by using stuff like pachyderm for model versioning and data provenance. So it can be extended, and we also have more, even more layers to the mix that Soila and Malini showed.
Thanks.
I have two questions here. So what were some of the challenges in separating, the architecture you had, where you had, Spark running on one side and then the inference engine? What was the challenge in integrating that with the Spark framework?
Okay, so the main challenge here that we're still addressing is the workflow orchestration. So if you have Spark running separate and you have your machine learning service running separately, one of the things you could do is just have your inference service running long term, and then your Spark service for inference comes and goes. But then you might want to couple the inference, the inference service and the Spark service, so you instantiate them together, and when one completes, so that whole life cycle management is something we're still addressing and trying to look at, what are the best tools that are available for us to orchestrate these workflows.
I was just wondering if it's possible
I just
to...
want to add a point to what Soila was saying.
Okay.
Our data center has right now 19 racks of machines, and we're dealing with 25 cars, bringing huge volumes of data. Drives could be about 4 hours to 8 hours long. So we anticipate down the road about a petabyte of data coming in each day. So if there are containers out there that are not really doing any work, especially when you're doing batch processing, we'd like to shut them down. If they're stream processing, it makes sense to have one instance of, the model service running, and then it grows and it shrinks. Let's say a whole bunch of data came in, and then it can expand to maybe 100 instances, and then when the cars are all done, all the data processed, it can shrink. But the life cycle point that she made is, if there's nothing happening, why not be able to close this and say, I've finished processing all my data, and I can use these machines and the hardware available there to do maybe something else in my data center, which might be simulation, which might be movement of data from our hot tier of storage or our warm tier of storage to our cold storage and things like that. So there's a lot happening in our data center, and our resources are important for us to recycle and reuse.
I was just thinking if maybe statically binding the IP addresses between two containers would be too much of a brute force approach. I don't know, but my last question
We
is,
might
Yeah.
not even need to do it.
No.
The beauty about Spark and Kubernetes, and this was, I think, a talk a year or two ago, what they did when the pod, when the RDD is there, they can look at which IP address it's hosted at, and that can be part of that whole orchestration of the actual pod with the executor. So you have that data locality.
right?
And given our data volumes, that was an important thing, and that was our motivation behind the monolithic solution.
My last question, what are the plans for integrating FPGAs for the inference pipeline?
What?
And
Plans to
FPGAs.
integrate
Oh, we have a talk
FPGAs.
tomorrow.
Yeah.
So that's a good plug for our talk tomorrow.
Oh, is that?
Carol is here, and he will talk about Movidius and FPGAs.
Very
Yeah,
sweet.
so
Yeah.
please come and join us tomorrow.
All right, sounds good, thank you.
Okay, thank you.
Thank you, everyone.